Okay, in this section we're going to talk about homomorphisms. Homomorphisms are quite similar to isomorphisms. Now iso means exactly the same, homo means like. So when you have two spaces that are related by homomorphism, they're not identical, but they're very similar. I can say that in a homomorphism, you lose some information about the original space. A typical homomorphism is a projection. If you think, let me just draw a picture of a projection. I know we'll get to this later, but just to give you a foretaste. If I have the xy plane and I project all my vectors in 3 dimensions onto the xy plane, I lose some information. I lose the information that's the z coordinate, but I do preserve some information. So in some sense, the xy plane is kind of represents some aspects of 3-dimensional space, but not completely. In the same way, a photograph can represent 3-dimensional reality, but not completely. So that's kind of the idea. A homomorphism preserves some properties of the original space, but it loses some properties. And we'll see how that plays out in the subsequent slides. All right, definition of homomorphism. Okay, now it has the same linearity properties that an isomorphism does. Okay, these two properties are called the properties that characterize a linear map. Now, two properties that it doesn't have, that an isomorphism has, is it's not necessarily one-to-one, and it's not necessarily onto. Okay, not necessarily onto. So that means that a homomorphism is not a bijection. But it does have the linearity properties. Okay, so let's go on and see what we have. All right, so here's an example. If I take h as a function of the second-degree polynomials, now this is an arbitrary second-degree polynomial. The coefficients a, b, c, and r are arbitrary. And I map this to a 2-dimensional vector in this way. Take the first coefficient plus the last coefficient and put that in the first entry and put 0 in the second entry. It turns out that this is a homomorphism. You'll have to verify the addition and scalar multiplication operations in a similar way that you verified that things were isomorphisms. So let's see how that works. All right, so here you're showing that h of the sum of two polynomials is going to be h of one polynomial plus h of the other polynomial. We'll see how that works out. All right, so h of the sum of two polynomials you can rearrange using the commutative and associative properties. Then you have a polynomial that looks like this. a1 plus a2 is the constant term, b1 plus b2 is the x term, c1 plus c2 is the x squared term. If you apply this rule to this new polynomial, taking the constant term plus the x squared term, well, here the constant term is a1 plus a2, the x squared term is c1 plus c2. We put that in the first entry here according to this rule. And we can break this vector apart by the usual rules of vector addition. And here we have h of the first polynomial, and here we have h of the second polynomial. So this verifies the property for addition. We also have to verify the property for scalar multiplication. Similar verification, if you take r times h of a plus bx plus cx squared, you can distribute in the r, and this is in fact the same thing as of h of r times a plus bx plus cx squared, because I can write this polynomial here as ra plus rbx plus rcx squared. And so h of this polynomial is ra plus rc, and that gives me the identification. All right, so everything works out fine and dandy. We do have a homomorphism. Okay. Now, here's another example of these two maps. The first is linear and the second is not. You can kind of identify linear maps. Linear maps are going to have the terms have to be linear in the sense that they're all first order in the variables. And I think you've seen examples where if the function has an x squared or an xy or y cubed or square root of y, it's not going to work. And also here you have a term with a constant. The term with a constant, that's also not going to work. This is an easy way to see that this is not linear. Well, let's see how he does it. Okay, the first map does respect addition and scalar multiplication. I'll leave you to verify that. But the second one does not respect addition. You can use some example like this. I guess the easiest way, usually the easiest way if there's a constant, you can show that it doesn't respect scalar multiplication. If you take g of 0 times anything, right, that should be, well, in this case, that's going to be g of 0, 0. But g of 0, 0 is equal to 1. And that's certainly not equal to 0 times g of 0, 1, g of 1, 0. Okay. So whenever you do have a constant in your expression, you know that scalar multiplication by 0 is going to mess up. Okay. All right, now when we looked at isomorphisms, we had two lemmas. An isomorphism certainly sends the 0 vector to the 0 vector. And we can actually use the very same proof to prove the same property for a homomorphism. A homomorphism sends the 0 vector to the 0 vector. So go back and look at your isomorphism proof. Use the same for homomorphism. Okay, another lemma. The following are equivalent for any map F from V to W between vector spaces. F is a homomorphism is one possible statement. An equivalent statement is that F of some linear combination of vectors is a linear combination of the F's of the individual vectors. So this should be familiar from isomorphisms. Okay. And then we extended that to an arbitrary number of vectors in linear combination, that F of an arbitrary linear combination of vectors is the same linear combination of the images of those different vectors. So in fact, we could prove the equivalence of these three conditions in exactly the same way we proved for isomorphism, because in the proof, if you look back, you never use the fact of one-to-one and onto in the proof. So you can just cross out isomorphism and put in homomorphism, you have the very same proof. Okay, so this is useful. Remember that to show something's a homomorphism, all you have to do is show that F of a linear combination of two vectors is the same linear combination of the images of those two individual vectors. All right, so here's one simple example. You can check that the 0 map is a homomorphism. Now, the 0 map is certainly not an isomorphism if V is if V is a non-zero vector space. But using this property too, I certainly have Z of any linear combination is going to be 0, but Z of each of the individual vectors is 0 also. So I do get the fact that the 0 is preserved under the linear combination. We do have a homomorphism. Here's another example. This is called the inclusion map. It's called the inclusion map because this is 2 dimensions, and we can think of 2 dimensions as sitting inside 3 dimensions as a plane. Now, this, you shouldn't confuse R2 with the xy plane, but it certainly can be identified with the xy plane. Okay. There's certainly a one-to-one onto correspondence between between R2 and the xy plane. Now, this is not an isomorphism because certainly I is not onto. Okay, I is not onto. But we do have one-to-one. And you can go through and show the homomorphism properties in this inclusion map case. I'll let you read that. I won't go through the details. All right, now here's another function. If I take the function from first degree polynomials to themselves, and I take h of a plus bx equals b plus bx, all right, and follow this. What this says is that no matter what the x coefficient is, I make that the coefficient of both the constant coefficient and the x coefficient. So here are some particular examples of how that works. And you can go ahead and verify that this function is linear. Again, I'm not going to go through this. We've done these steps many times. All right, the derivative map is another example. Here we're doing the derivative map on this particular polynomial space, on second-degree polynomials. In fact, it turns out that the derivative map is homomorphism on no matter what polynomial space you have. But in particular, if we restrict ourselves to second-degree polynomials, the derivative map acts on a second degree, that is a quadratic polynomial, in this way. And here we have some examples, and we can show in similar way that this map acts linearly. Again, I'm not going through the details. You should be able to verify this by now. Here's another example, the trace of a square matrix. Trace always means the sum of the diagonal entries. Here we're just seeing trace of a 2x2 matrix, but if you had a trace of an n by n matrix, you just sum right down the diagonal, however many diagonal entries you have. And again, you can verify these steps that in fact trace is a homomorphism. All right, so here's an important theorem. A homomorphism is determined by its action on a basis. Okay. All right, so to make this more specific, if V is a vector space, so let's draw a picture here. Let's say V is R3, and we have some basis sitting in R3, which basically means three vectors pointing in independent directions. You have to think that these three vectors are not supposed to be in the same plane. Okay. Now, if W is another vector space, and here I have n vectors in W, and these elements don't need to be distinct, then there exists a homomorphism from V to W that sends each beta I to Wi, and that homomorphism is unique. So here I have my R3. This is a basis of R3. Let me draw a better basis. Why don't I just draw the usual basis so you can see more clearly what's going on. Okay, so I'm going to draw the usual basis. Okay, usual basis here. Okay. So I can call this beta 1, beta 2, and beta 3. And this maps under, we want this to map to three different vectors. Now, in fact, these three different vectors could be in the same plane. We don't know. Okay, sorry. Right. Okay, three vectors here, W1, W2, and W3. And the point is that if I know that B1, if I know that B1 maps to W1, B2 maps to W2, and B3 maps to W3, then that actually determines what any vector here maps to. Now, the idea is that if I take any old vector in this original vector space, I can treat it as a linear combination of these three betas. And then I'll use linearity to find the homomorphic image of this vector by using the properties of preservation of linear transformation. All right, so let's see how that works. Okay. All right, so for any input vector V, let its expression with respect to the basis be V equals C1 B1 plus ... plus Cn Bn. Since the betas are a basis, I can express any vector in the input space in this way. Sorry, sometimes I say B, sometimes I say beta. I think you understand what I mean. All right, now let's define the associated output by using the same coordinates with H of V is equal to C1W1 plus CNWN. Okay. This is well defined because with respect to the basis, the representation of each vector V in the domain is unique. Okay, so I take any vector in V, I can express it uniquely in terms of the basis, and then I can uniquely define a H of V in this way. You can show that this map is a homomorphism. You see that really I have chosen H of V in just such a way as to preserve the linear property. I'm saying that H of this linear combination of betas is just the linear combination of the W1 through Wn, and W1 is H of beta 1, Wn is H of beta n. Okay. So in fact, this will preserve linear combinations. He only showed a linear combination of two vectors because, as we showed, if it works for two vectors, It will work for any number of vectors. All right. The map is unique because if I had another homomorphism that also satisfied this same property, that h of beta I is equal to wi, then h and h hat have the same effect on all vectors in domain, because h hat of v, I could express v in terms of this basis. By the linearity property, h hat operating on this basis should be equal to a linear combination of the images of all the beta i's. However, I have to have that beta hat sends that h hat sends beta I to wi. So I know that h hat of beta I must be wi, h hat of beta n must be wn. And this is what I defined h of vn to be. So the upshot is I can't escape if I want to have a homomorphism that maps basis vectors to a set of particularly specified vectors. There's only one possible homomorphism that does that, and I can define it. I can define it in this way. Okay.
Yeah.
Okay. All right. Now let V and W be vector spaces, and let B be a basis of V. A function defined on that basis can be extended linearly to a function on the entire vector space V if for all vectors in the vector space V, such that V is a linear combination of these basis vectors, the action of the map is f hat of V is the linear combination of the corresponding images of the different basis vectors. In other words, you're just applying here the definition up here, that the fact that if you have the function f defined on the basis vectors, there's a unique linear extension to all of the vectors in V, and it's defined in this way. And it's basically defined in order to make sure that the linear property will be satisfied. Okay, let's see where we go from here. Okay, so here's an example. On the basis of the space of quadratic polynomials, I have a basis which consists of x squared, x and 1. We've seen this basis before. This is the standard basis. I could define a mapping suggestively called eval, that maps, eval3 rather, that maps second degree polynomials to a real number by specifying its action on the basis x squared, x and 1. Now, why is he calling it eval? He's saying he's really saying, what do you get when you evaluate a polynomial setting x equal to 3? Now, if I set x equal to 3 and plug that into x squared, I get 9. If I set x equal to 3, plug that into x, I get 3. If I set x equal to 3, plug it into 1, well, it just remains 1. So if I extend linearly, then eval3 of any second degree polynomial, just work out the algebra here, it's going to be 9a plus 3b plus c, which is exactly the value of this polynomial when x is equal to 3. We've extended this definition from x squared, x, and 1 to any second degree polynomial. Here's another example. Consider the standard basis. Standard basis is this one, 1, 0, 0, 1. And you can specify a rotation of these two basis vectors. You can work this out by trigonometry. If I rotate 1, 0 by an angle theta, the components of this vector here are going to be cos theta, sine theta. So that's a trig exercise for you. On the other hand, if I take the vector 1, 0 and I rotate it by angle theta, another trig exercise will show you that the x component is minus sine theta. You can see in this case the x component is negative, and the y component is cos theta. Right? So if I rotate these two basis vectors, I can get these two individual results. Now, since rotation is a linear map, you can think about why that is. Once I've specified the rotation on two vectors, it's actually specified on any possible vector. So we have, to extend linearly, we'd have that the rotation, which I'm denoting by t theta. Well, if I take t theta of any arbitrary vector xy, I can write that as a linear combination of the two basis vectors. So the rotation on xy is the corresponding linear combination of the images of the two basis vectors, and I get this result here. You can actually write this as cos theta minus sine theta, cos theta times xy, which shows that we can represent this homomorphism as using a matrix, and we'll come back to that later. A special case of a homomorphism is a linear map from a space to itself. And this is called, in this textbook, it's called linear transformation. And in the textbook, he noticed this, that other authors don't always use this notation. But in this textbook, that's the notation that's used. So we're assuming that both the domain and the codomain are the same vector space. In that case, we call this a linear transformation. One example is the identity map. We've already shown the identity map is an isomorphism, and isomorphisms are linear transformation. Isomorphisms are linear maps. So in this case, it's a linear transformation. And you can check that this reflection map is also a linear transformation. What does reflection do? Think about it. If I have my three coordinate axes, x, y, and z, and if I have suppose I'm along the x-axis here. Well, any vector along the x-axis is going to be reflected in the zy plane. So what this map does is it's as if the zy plane is a mirror, and it maps the vector to its corresponding vector on the other side. And you can verify that this reflection map is in fact a linear map. Since it's a linear map of R3 to itself, it's a linear transformation. Okay. So lemma. For vector spaces V and W, the set of linear functions from V to W is itself a vector space. Now this is quite remarkable, and it's a common strategy in mathematics. You define a mathematical structure, and you iterate the process. You define mathematical structures on top of mathematical structures. And really there's no end to it, and it can get very confusing, but also this type of thinking is very, very powerful. And you can prove very deep results by thinking in this way. Okay, so in other words, we are now thinking of linear maps. You need to think of maps themselves as vectors. Okay, now this may seem very difficult if you think of vectors as arrows, but remember we also have thought about functions as vectors. Okay, so the vectors don't have to just look like arrows. And we denote the space of all linear maps from V to W by script L of VW. Right? And we'll prove this lemma shortly, that in fact the set of linear maps from a vector space to another, the set of all possible linear maps is itself a vector space. So the proof, all right, the set of linear maps is non-empty because it contains the zero homomorphism. We know if we map all of V to 0, that is a homomorphism. And of course, W has to have 0 because it's a vector space. Okay. So in order to show that, in fact, the linear functions are a subspace, we only need to check that it's closed under the operations of plus and scalar multiplication. So let F and G be linear maps from V to W. Okay. Then the operation of function addition is preserved. We can verify that here. If you take F plus G acting on a linear combination of vectors, I can write that as F plus G. It's the corresponding linear combination of F plus G acting on the individual vectors. What does that mean? If F is linear and G is linear, then F plus G is also linear. Okay, so if I'm treating this f and this g as vectors, then if I have linear vector here, linear mapping here, the sum of those two linear mappings is itself a linear mapping. The other thing we have to show is the scalar multiple times a linear map is itself a linear map. And to do that, we verify the linearity property on the scalar multiple times the linear map. And we've done things like that before. So we've shown that linear maps are closed under addition and closed under scalar multiplication. So in fact, they're a subspace of the space of the vector space of all functions from V to W. Okay, very important result. Here's an example. Consider all linear maps from R to R squared. Let's fix a basis for these two spaces. Okay, let's use the easy basis. The easy basis of the real numbers would just be the number 1. Okay, because that's an element of the real numbers. The easy basis of the R2 would be the natural basis, the 2 coordinate vectors. Now, if I can certainly define a linear map this way, I can define for any fixed constants C1 and C2, I can map 1 to C1 times the first basis plus C2 times the second basis. Now this C1 and C2 are fixed for this particular mapping. So for instance, if I was going to map 2, I would extend this mapping linearly. Okay, so 2 would go to 2 times C1 times 1, 0 plus 2 times C2 times 0, 1. So we can actually write any such linear mapping from R1 to R2 in this way. So any constant C1 and C2 determine a unique linear mapping. Okay? So C1 and C2 are like two components of a two-dimensional vector space. So the set of all possible linear mappings from R1 to R2 is a two-dimensional vector space. Okay, let's look at this case. If I take linear mappings from R2 to R3, I fix a basis of R2 and a basis of R3. And remember, we talked already about how a linear mapping is determined by its action on the basis. Okay, so if I determine that E1 in the basis for R2 maps to this particular vector in R3, and E2 maps to this particular vector in R3, then that will determine uniquely the linear transformation that maps E1 and E2 to these two different vectors. Okay? So how many dimensions are there? Well, the linear transformation is specified by 1, 2, 3, 4, 5, 6 arbitrary constants. We have 6-dimensional vector space. Okay. Now, do you see the generalization here? When we had R1 to R2, we had a 2-dimensional vector space. We have R2 to R3, we had 6-dimensional. See if you can see what the pattern is here. But notice that for each vector in the basis of the domain, there's going to be a number of arbitrary constants equal to the dimension in the codomain. Okay, so each time I have a vector in the domain, I'm going to have, in this case, I'll have 3 constants. So you have to think about there's some multiplication going on here. We'll see it explicitly shortly. Okay, I'm going to stop and we'll pick up in the next video.